Good morning, students. Welcome to Real Analysis Live Lectures. In this lecture, we'll discuss about continuous functions in a metric space. Okay. So let's start the definition of a continuous function. Okay. So take two metric spaces m comma d and n comma rho. These are two metric spaces. A function f map from m to n. So suppose this is m and this is n, and this is a map f mapping elements of m to n. We say that this f is continuous at this point x naught if given any epsilon greater than 0. So there exists delta greater than 0 such that whenever d of x naught is less than delta, then rho of fx naught should be less than epsilon. So what is this one? Is that so we say that f geometrically f is continuous at x naught if given any epsilon. What is meant by saying rho of f of x naught less than epsilon is same as saying that you take for this x naught, consider your f of x naught. Okay, then consider a ball around epsilon, ball around f of x naught around with radius epsilon. Okay, so suppose let me write. Okay, okay, this is ball of distance epsilon. Then what is meant by saying this is continuous? In this situation, we should able to find some delta such that any element in this ball. So if I say this is delta, if I take any x here, then this f of x should be mapped to some point this f of x in this ball. So whenever you have some point x in this ball, then its image should be there in this one. Okay, so we should able to find, if we can able to find some delta such that for every x in this ball, f of x is there in this ball, then we say that f is continuous. Okay, so I repeat again. Given we say that f is continuous at x naught if find a given any epsilon. So take a ball around f of x naught of given epsilon radius, then we should able to construct a ball around x naught here, okay, of say radius delta, such that whenever a point is there in this ball, then its image should be there in this ball. Okay, then we say that if such condition is satisfied, then we say that f is continuous at x naught. Okay, and if it is continuous at every point, then we say simply say f is continuous on the metric space m. Right, fine. If you understand this one, that is what I have written here, right? So f of x, f is said to be continuous at x naught if, so what is this one, d of x comma x naught is less than delta implies rho of fx naught is less than epsilon, right? This is same as saying that as I explained here, ball, this x belongs to ball around x naught. Okay, so you can mention this is here. This is same as saying that f of x is in ball around f of x naught, okay, of epsilon radius. This metric we didn't by rho, but this is same as saying that whenever x is there, its image is there. That means f of this ball, okay, is contained in ball around this f of x naught. Okay, so equivalently we can use these versions. One is this one, or this is same as prove here is same as all are equivalent, right? Okay. Before going to some examples and all, we give some equivalent conditions of a continuous function in terms of convergence sequence, in terms of open sets, and in terms of closed sets. Okay, so start with f metric function from m comma d to n comma rho. Then we say that f is continuous on m is same as saying that for any x in m, if at all is a sequence xn converges to x, then we should have f of xn should converge to f of x. Of course, this is in M and this is in N, right? So this is the characterization of continuous function in terms of convergent sequences. So we say that f is continuous at a point if at all is any sequence xn converging to that point, then f of xn should converge to f of x. And in terms of closed sets, if whenever you have f is from M to N, so whenever you have a closed set E here, then f inverse of E should be closed. So whenever this is closed, implies this f inverse of E should be closed. Similarly, it is for open also. So whenever V, if you have V is open, then if you take its inverse image, f of V should be open. If it is true, then you can say that f is continuous function. Okay, proofs are not so difficult. We can quickly go through it. It is not at all difficult one. uh, I will try to explain the overview. Suppose this f is continuous means by epsilon delta definition. You can call it this is epsilon delta definition. This is in terms of convergence. So assume epsilon delta definition of continuity. Then we want to prove that if at all xn converges to x, then f of xn converges to f of x. Very simple. So start with the sequence xn converging to x, then we want to show that f of xn converges to f of x. So whenever we want to show some sequence converges, start with epsilon greater than 0, then somehow find some delta satisfying certain conditions, right? So start with epsilon greater than 0, right? Then somehow we should get a delta. How we get that delta? That delta we get it from this xn converges to x, right? So for this xn converges to x and we started with epsilon greater than 0, so there exists delta greater than 0 such that this uh, uh, sorry, using this f is continuity. Okay, f is continuity for this epsilon greater than 0, there exists delta greater than 0 such that whenever this distance between x comma y is less than delta, then what we have is rho of f of x comma f of y is less than epsilon. Okay, now for this delta we will apply the xn converges to x, right? So because xn converges to x and we have delta greater than 0, so there is some stage n such that distance between xn comma x is less than delta for all n greater than or equal to n. Now applying this definition, that shows that rho of f of xn comma f of x is less than epsilon after this stage for all n greater than or equal to n. But this is same as saying that f of xn, this converges to f of x, of course, in n. So proofs are not difficult, follows simply by what is given and how we will apply it. Now 2 implies 3. What is meant by saying 2 implies 3? If at all we have a sequence xn converges to x, then we can guarantee that f of xn converges to f of x. This is our, under this assumption we want to show that whenever E is closed, then f inverse of E is closed in A. So start with a closed set E. So let E be a closed set. E be a closed set. Then we want to show that f inverse of E is closed in A. Right? So to show that f inverse of E is a closed in M, we'll try to recall a statement. Okay, when we say something set is closed, so take a sequence xn, okay, in F such that xn converging to x in M, okay, then show that x is actually coming from F. This implies F will become a closed set. So that result we will be applying here. So we want to show that f inverse of E is closed. So take a sequence xn in f inverse of E. So start with a sequence xn in f inverse of E, right, such that xn converging to some x where x is in that metric space M, and finally prove that x is in f inverse of E, right? Then we are done. F inverse of E will become closed because xn's are in f inverse of E is same as saying that this is small. Okay, so f of xn's are in E and E is given to be closed set, right? And because we have now there is a sequence xn converging to x, by the assumption of 2, what we get is that f of xn converges to f of x. Okay, so you have a sequence and this is a closed set converging to some point. that means this f of x is actually belongs to E, right? That shows that x belongs to f inverse of E, and that is what we are supposed to prove it. That shows that f inverse of E is closed. Okay, so if we write it things in proper way, proofs are not at all difficult one. Okay, you can go through it again here. Now this is very obvious. Open and close, 3 implies 4. So just use the inverse images and so on. You get this. What is you want to show that 4 implies 1. That means whenever f inverse of V is open implies f inverse of V is open. If it is true, then we want to show that f is a continuous function, right? F is continuous. So we show that f is continuous at every point. So to start with, let x belongs to M. Okay. Now, when we can use this fourth statement, if at all we have some open set, then its inverse image is open. That much we can claim, right? So this f is a map from M to N. We started a point with x in M. Now, can we get some open set in N is the question. Obviously, f of x belongs to N is there, right? So if we can get some open ball here, then we can apply the fourth condition to get some open ball in or open set in M, right? That is the idea. Okay. So by epsilon delta definition, we want to show that this f of f is continuous. So start with x belongs to M and epsilon greater than 0, right? So if we have a point and if you have an epsilon, obviously you can have a ball f of x around f of x of this epsilon that is here, right? So this is a, what do we know? We know that this is an open ball, so it is an open set in N. Therefore, by 4, f inverse of V is open in M. That you can now see here. So therefore, this f of x, this one is open in M. That means f inverse of this one is open in M. For simplicity, we will write this V as V of f of x. Okay. Then, if you write this one, obviously f of x belongs to here because f of x belongs to that ball. That shows that x belongs to f inverse of V, right? Now we know f inverse of V, this is open and x is a point there. So therefore, there exists a ball of some radius. You can call it delta. So ball around x of radius delta is contained in, you can write this as a metric D, is contained in f inverse of V. But this is same as saying that what? F of ball around x of delta, this is contained in V. But our V as a notation is nothing but ball around f of x, okay, of radius epsilon, of course in metric rho, right? But this is precisely what you want to show is nothing but this means your f is continuous. Okay, if you recall, here we have written 3 equivalent statements for this continuity, and from this one it follows, right? Okay, this is, so what we have just now proved is that this f is continuous, okay, if and only if whenever you have xn converges to x, then f of xn should converge to f of x. This is also same as, okay, another way we have proved is that whenever V is open in M, then f inverse of V should be open. This is of course, sorry, N. Then f inverse of V should be open in M. It's also equivalent proving that if V, or you can say call it E or whatever, E is closed in N, then f inverse of E is closed in M. So any these 3 we can use for continuity, right? Now we can quickly one standard example which everyone might be knowing, this characteristic function of q, that means chi q of x, which is 1 if x is a rational number and 0 if x is not a rational number. Okay, we can show that it is nowhere continuous. That means at no point this function is continuous. Okay, how we can prove this? We'll show that if x is a rational number, at every rational number this function is not continuous. Also at x, for every x which is irrational, that means r minus q, also this is not a nowhere continuous. Okay, fine. So start with x is in Q. So if x is in Q, then what is the value of chi q of x? This is 1, right? And of course, if you take a ball around 1 of radius half, then obviously one is there in here, so 1 belongs to here. That means your chi q of x belongs to here. That shows, that is same as saying that x belongs to chi q inverse of this ball. Okay, right? Okay, now you can see that for every x in Q, we proved that x is also here. That means Q is contained in chi q inverse of, that means here, right? So entire Q is contained in this ball, not sorry, not ball, chi q inverse of this is a set, right? Now what you can observe here is that not only this, you can also show that every element here is also here. By taking y belongs to here, then chi q of y is here, but chi q of y either takes value 0 or 1. But if it is 0, then it cannot be in this ball, because distance between 0 and 1 is 1, which is not less than half. So this value has to be 1, which shows that y belongs to Q. So what we proved is that Q is, you can represent inverse image of this ball around 1 of radius half, right? Now we know that Q is not open, so this is not open. Because it is not open, this cannot be open, so this is also not open, right? So what we have proved, if at all chi q is continuous at x, right, we know that this ball is open. Okay, if this ball is open, then its inverse image should be open if at all it is continuous. That shows that chi q is not continuous at any x which is a rational. Same way, we try to show that this is not continuous at any irrational point. So there, by selecting suitable ball, obviously you select this ball around 0 of radius half, then this x belongs to here and so on. You do it same way, we can conclude that it is not continuous at any point, right? The another interesting example is that any map any map defined on n to r is always continuous, no matter what that function, how that function is defined. Okay, it's a very quick proof. If you want to show that it is continuous, start with any point, show that this if you take any epsilon greater than 0, then we want to show that uh, the using in terms of balls, we can show that ball. So find some delta such that this one, okay, is contained in ball around f of n. Okay, you can call it this rho of this epsilon, right? So how we can find, so find delta greater than 0 such that we want to show this, right? But it is very tricky or simple. Can you find some delta in such a way that this b of n is such a way that this f of this one is always here? And that is true if we find delta is equal to half or anything less than 1, for example. Then what is this ball around n of distance half is what are all in n what are all natural numbers satisfying this condition is only that one, right? So you to have two natural numbers, at least their distance should be greater than 1, right? So because of this, you will get that f of n is contained in ball around f of n, right? So therefore it clearly follows that f is continuous. Okay, so no matter what function it is, if it is defined on n to r, then it is always continuous. And exercise prove that this map is from r to n, then this is continuous if and only if it is that function has to be constant. That means if you take any non-constant function from r to n, then it is not a continuous function. Okay, try to show that by taking something. If you are not getting, you can ask me, I can explain in next class. So from r to n, if at all, what are all continuous functions? Only constant functions. No other non-constant function defined from r to n is not a continuous function. Okay, fine. If you take a continuous function from r to r, then if you take this set x such that f of x is strictly greater than 0, then you can show that it is an open set. And you also have f of x equal to 0, then this is a closed set. it is not at all difficult one to prove. If at all we want to show that it is an open set, if you understand f of x greater than 0, this is same as saying that f of x belongs to 0 to infinity. That is same as saying that x belongs to f inverse of. So this set x such that f of x greater than 0 is same as saying that x such that x belongs to f inverse of 0 to infinity. That means this set is obviously f inverse of 0 to infinity, right? But f is given to be continuous function and 0 to infinity is an open set, so f inverse of open set is open. Similarly, what is f of this x such that f of x is equal to 0? This is all nothing but f inverse of singleton 0, right? F inverse of singleton 0. So since singleton 0 is closed, so therefore this is closed because our f is continuous, right? Okay. And there is a also it's two metric space m comma d and n comma rho. If you take, then a map f between them is called an isometry if it preserves the distance. What is meant by saying that f preserves distance? Means if you take two elements here x and y, so distance between x comma y, then you take their images, so what you get here is f of x and f of y, so their distances should be equal. If it is true for every x and y in M, then we say that this is an isometry. A simple exercise, very basic exercise to show that every isometry is continuous. Okay, that means by just this definition it follows, if you take your delta as epsilon, you are done, right? Or just write it clearly, you will get it. Fine. Now we'll try to define, if you have a metric space M and you have somewhere this is a set A, okay, then we try to define what is meant by, if you take a point X in M, what is distance from this element to this set A. So distance from X to A, how we can define. So obviously the sense is try to find all points here and find the different distance between x comma a and find the smallest one, that means infimum. So distance between x comma a we can define as infimum of distance between x comma a for every a in a. Okay, and obviously one can observe that if this x, whatever this x is already here, then distance between x comma a is 0. Okay, right? But converse is not true, that you can check here distance between x comma q is 0, but x for every x in q, but if you take irrational number here, that belongs to here, right? So when, if distance between x comma a is 0, if at all it is not belongs to that set, but what we can guarantee is that it is in at least closure of that set. Okay, so distance between x comma a is 0 if and only if x is in closure of that set. Okay, and proof is not at all difficult. It is only if you understand what is meant by infimum of some set. Okay, infimum of some set A is alpha, right? If this is means infimum means greatest lower, right? So if you take any epsilon greater than 0, this is the greatest lower bound. That means alpha plus epsilon, it is no more a lower bound, is not a lower bound. So if it is not a lower bound means what? This implies there exists some x in A such that alpha plus epsilon is not a lower bound. So that means x is less than alpha plus epsilon. If you remember this, this is true for every epsilon greater than 0. So if you recall this statement, then this is your set and infimum is 0 here. So your alpha is 0 here, right? So if you take in particular epsilon is equal to 1 by n, then alpha is 0 here means what? 1 by n, 0 plus 1 by n is not a lower bound for that set, for this set, right? But what is meant by saying that there exists some an element here. What is meant by saying an element here? There is some element here that we are calling as xn. So distance between x comma xn is actually an element. Okay, this is strictly less than alpha plus epsilon, that is 1 by. Okay, that is what we are writing here. Okay, right. So infimum of this set is 0 is same as saying that for every epsilon is equal to 1 by n you have this condition. But this is same as saying that xn converges to x, right? Xn converges to x where xn's are in A, and that means xn belongs to, sorry, what is the there is some typing mistake here. This is not correct. So xn's converges to x where xn's belongs to A, right? So that means you can show that x belongs to A bar, right? So we have already proved a result that x is in A bar if and only if there exists a sequence xn in A converging to x, right? So this not xn, this is x. And you can go up also same. So it is if and only if condition, right? Fine. Now this dx comma a is actually a function, and you can say that it is a continuous function, right? So what is the statement? You take a subset of m and then f maps from m to r defined by any f of x you take, then you find distance from that x to this given set a. Okay, you can show that this function, you can call it as a distance function. If you want, you can call it this as a distance function. We are measuring distance of each point from the set A. Okay, this is continuous. Proving something again continuous is what we want to show. Take epsilon greater than 0. Okay, then we want to find some delta such that whenever distance is 2, then there is also there, right? So for that, it is enough if we show that distance between x comma y minus distance between y comma a for any x comma y in M, there is, so what you just go here, so take another point y here. Okay, sorry, not outside. So take some x here and y here, then try to find distance from x to a and from y to a and take their difference. Okay, that we always show that it is less than or equal to this distance between x and y. So we can easily show that it is not a difficult one with the simple calculations and using triangle inequality. And once it is there, then your whatever epsilon you take, delta will be the same epsilon you take, that will be your delta. Okay. So these are the basics things using, of course, using triangle inequality for any a in A. What is d of x comma a? Introduce y here. So d of x comma y plus d of y comma a for every y in M. Then because a is here, you can take infimum of such things. So infimum of this is less than or equal to infimum of that, but this is nothing but d of x comma a, right, is this, and you bring here. Similarly, by replacing the role of x and y, you can prove this, right? By taking delta as same as epsilon, you can show that this f is continuous. Okay, right? So that distance function is a continuous function. You can easily see that whenever you have this f maps from m to r, then this x, which already we have proved, x says that f of x is equal to 0. This is closed. Last time we have discussed, because this is nothing but simply f inverse of the singleton 0, right? Conversely also one can have, means if at all you have e, which is the 0, e is the 0 of the function. So if at all you have such that x says that f of x is equal to 0, then uh, and what is that f here? F of x is nothing but d of x comma e. This is always continuous, which we have just now seen. So let me say this one. What we have here is, if we have a continuous function f maps from m to r, then we always have that all points close going to 0, it is always a closed set. And whenever the conversely also, if you have a set E which is zeros of this function, particular function, then that function is always continuous. That means we can define a function such a way that E which is zeros of that function is continuous, right? Next point will come, which is homeomorphism. Okay, so far what we have seen is f maps from m to n is continuous. Okay, and the homomorphism is you take a function f maps from M to N, which is a bijective map. Then we say that two metric spaces M comma D and N comma rho are homeomorphic if there exists a bijective map. Okay, so this is a bijective map such that f and f inverse both should be continuous. So if f as well as f inverse both are continuous, then this M and N, they are said to be homeomorphic, and such f is called a homomorphism. Okay, so whatever results we have seen so far for continuity, applying for f inverse, which is also continuous, you will get more conditions. Okay. Fine. You can check that if f is a homomorphism, then obviously f inverse is also homomorphism. Every metric space is homomorphic to itself, right? uh, Take this interval 0 close open 0 and closed 1, and the other way you can take 1 to infinity. Okay, you take any point x here, that means it is like this. Then how we can send something here? What should be your f such a way that this x can be sent here? Obviously 1 by x if we take, then you can check that it is a bijective map, continuous, and so on. So x sending x to 1 by x gives a homeomorphism between 0 comma 1 to 1 to infinity. Okay. So try to complete the details. Okay, why this is continuous, and then in x in inverse is continuous, and so on. Okay. If you take any two intervals of same kind, say suppose a comma b and c comma d, okay, in R, then you can have a map from here to here in such a way that that I have defined here. F of x, any x you take here, you simply send c plus because it should belongs to here, and m minus x minus a. Okay, where our m is nothing but b minus c by b minus a. So if you take this, then you can first of all check that this f is well defined, and obviously f is continuous, right? As a polynomial, you can check this, and f inverse, find out f inverse and make sure that it is continuous, right? So therefore any two intervals of same kind, they are homeomorphic to each other. Fine. And some of the exercises I have given here, try to verify. If you are not getting, you can ask. Even though if you are taking same set, but if metrics are different, so suppose r comma usual and r comma discrete, if you take, they are not homeomorphic. So they are not homeomorphic. Why? Because in discrete space we know every set is open, whereas in usual it is not that every set is open or every set is closed like that, right? So you can easily see that if at all these metrics are homomorphism, then f maps from R to R is bijective such that f and f inverse are continuous, right? So you know that this f of x, so take x here, then take this f of x, right? Here you have discrete. Okay, so therefore what we know here is every set is open here, so singleton f of x is open in this discrete metric space. So if at all this is a function is continuous, then f inverse of f of x, because it is bijective, what you get here is that x, right? But we know that the singleton is not open in R with usual, right? That shows that these two cannot be homeomorphic. Okay. So if you quickly go here and see for continuity, we have given four equivalent conditions. One is epsilon delta here. One is epsilon delta, and the other one is in terms of sequence. The other one is in terms of closed and open. For f being continuous. So same thing you can apply for f inverse being continuous. You get different things. So if f is a homeomorphism, this whatever you have here, it will become if and only if statement. Okay. So proof follows similar, that if f is a bijective map, so if you take f, okay, a bijective map from m comma d to n comma rho, then the following are equivalent, saying that f is a homeomorphism is same as saying that whenever you have for all xn, suppose xn converging to x, then f of xn converging to f of x. This we already seen if it is a continuous function. So what if at all it is a homeomorphism, then the other way is also true. That means whenever f of xn converges to f of x, then xn also converges to x. Similarly here, if G is open, what we proved earlier is that f of G, or earlier what we have proved is that whenever G is open, then f inverse G is open and so on. So now what you can do is that G is open, then f of G is open in N. Okay. Similarly, if E is closed, then f of E is closed in N. Okay. So f is a homomorphism if and only if any one of this is true, right? And again, proofs is not at all difficult one. Every time we have to take the help of f and f inverse being continuous and using the fact that f is bijective. Okay, so using these factors we can prove it. So quickly see how this one. Suppose f is a homomorphism. We want to show that whenever xn converges to x, f of xn converges to x. This simply follows by f is being continuous. Conversely, suppose f of xn converges to f of x. We want to show that xn converges to x using the fact that f is a homomorphism. Because f is a homomorphism, then f inverse being continuous, what we know is that f inverse of f of xn converges to f inverse of f of x, right? But f inverse of f, because f is bisective, is same as this xn converges to x, right? F inverse composed f is identity, right? So xn converges to x. Now 2 implies 3. What is meant by 2 implies 3? That xn converges to x implies f of xn converges to f of x, and f of xn converges to f of x implies xn converges to x. So with this assumption, we can easily check that f is continuous. Why f is continuous? That is obviously clear. Xn converges to x implies f of xn converges to f of x. This implies f is continuous. But to show f inverse is continuous, okay, f inverse is a map from M to N, right? So take a sequence, call it yn converging to y. Our claim is to show that f inverse of yn converges to f inverse of y, right? But because this map is a bijective map, this yns can be written as f of xns, and this y can be written as f of x. So what we have here is f of xn converges to f of x. So therefore, by assumption, what we have is xn converges to x. But what is xn? If yn is f of xn, then xn is f inverse of yn, converges to f inverse of y. So what we have proved is that if yn converges to y, we proved that f inverse of yn converges to f inverse of y. So therefore, f inverse is also continuous. Okay. Now, to prove 3, start with G open set. We want to show that f of G is open. Okay. So let G be an open set. Then using the fact that f inverse from n to m is continuous, and we have G here which is open, this implies what we get here is inverse image of this function, okay, of this G is also open. But f inverse of inverse is nothing but f, so f of G is open in N. Conversely, if we assume f of G is open, f of G is open and f maps from M to N. So you have here f of G, which is an open set. So f inverse of f of G, and using the fact that f is continuous, this should be open in M, right? But what is f inverse of f of G? Is G. In that way, you can prove it. It is not a problem. And this open and closed, I skip, you can do it, right? The other one, by assuming that this closeness property, we want to show that f is a homomorphism. That means f and f inverse are continuous. That is what we want to show. So to show f is continuous, f maps from M to N. If at all we want to show it is continuous, in terms of closed sets, what it is enough to prove what? Take E, anything closed set in N, show that f inverse of E is closed. So this is our aim. If we can prove this, then f becomes continuous, right? Start with E. E is a closed set N, but E can be written as f of f inverse of E. So therefore we have something f of some set is closed in N. That means that inside whatever we have is closed in M. So that means F inverse of E is closed in M. That is what we want to prove, right? So it is very simple. Just you have to rewrite things properly and see what is there. To show F inverse is continuous, so F inverse is a map from N to M. So start with some closed set here and show that its inverse image, that means F of this one. We want to show that this is closed in N, right? So being F is closed, then by using that criteria, whatever assumption, we know that F of E is closed. Okay, this you can say this is E, right? But that is same as saying this one. Okay, so that shows that F inverse is also continuous. So we have just now seen the characterization or equivalent conditions for homeomorphism. And what all we have here is simply the I can say algebra of these continuous functions and so on. That means if f maps from L to M and g maps from M to N are two functions such that f is continuous at A and g is continuous at f of x, f is continuous at x and g is continuous at f of x, then g compose f is continuous at g compose f is continuous at x. Okay, that means it is simply nothing but composition of two continuous functions is again continuous and so on. Okay, proofs and all, what we argue here is in terms of sequences. If xn converges to x, if f is continuous, then f of xn converges to f of x, right? So you want to show that g composed f is continuous at x, so start with a sequence xn converging to x, right? Then use the fact that f is continuous at A and g is continuous at f of x and get the conclusions. Okay, fine. This space of continuous functions, what is meant by space of continuous functions? So take m comma d, which is any metric space. Okay, then you denote this C of m, all continuous functions defined from M to R, f is continuous. Okay, this we can make it as a vector space by defining two operations, namely f plus g is nothing but f of x plus g of x, and some scalar times a of x is find f of x, then you multiply that to a, which is defined in R, right? With respect to these two operations, it will become a vector space and it is called the space of continuous functions, right? And you can check this is again if f and g are two continuous functions, this is just like extension to this previous result, then you can see that f plus g, f minus g, f times g, a times f scalar times minimum of these two continuous functions. Okay, then maximum, all these things, even if g is, suppose if g is non-zero, then f upon g, that means whenever f upon g is defined, these are all continuous functions. And how we prove it? Again with the help of convergence, that means xn converges to x. If at all you want to show that f plus g continuous, then take this f plus g of xn, show that it converges to f plus g of x with the help of f and g being continuous. Okay, so this proof is not at all difficult, I just skip that and use this maximum of f and g, this formula you should understand better, and minimum of this one. Okay, minimum and maximum, if you understand, it is very easy to get it. So this is about continuous function. In next class we'll discuss about connectedness, which is an interesting point. Okay, we'll stop here and we'll meet in next class.